Until the End of Time by Brain Greene. Chapter 2. The Language of Time, Past, Future, and Change. On the evening of January 28, 1948, nestled between a performance of the Schubert Quartet in A minor and a presentation of English folk songs, BBC Radio broadcast a debate between one of the most potent intellectual forces of the 20th century, Bertrand Russell, and Jesuit priest Frederick Copleston. The topic, the existence of God. Russell, whose innovative writings in philosophy and humanitarian principles would earn him the 1950 Nobel Prize in Literature, and whose iconoclastic political and social views would earn him a pink slip from both Cambridge University and the City College of New York, provided numerous arguments for questioning, if not rejecting, the existence of a creator. One line of thought that informed Russell's position is relevant to our exploration here. So far as scientific evidence goes, Russell noted, the universe has crawled by slow stages to a somewhat pitiful result on this earth and is going to crawl by still more pitiful stages to a condition of universal death. With such a bleak outlook, Russell concluded, if this is to be taken as evidence of purpose, I can only say that the purpose is one that does not appeal to me. I see no reason, therefore, to believe in any sort of God. 2. The theological thread will be stitched into later chapters. Here, I want to focus on Russell's reference to scientific evidence for a universal death. It comes from a 19th-century discovery with roots as humble as its conclusions are profound. By the mid-1800s, the Industrial Revolution was in full swing, and across a landscape of mills and factories the steam engine had become the workhorse driving production. Nevertheless, even with the critical leap from manual to mechanical labor, the efficiency of the steam engine, the useful work performed compared to the quantity of fuel consumed, was meager. Roughly 95% of the heat generated by burning wood or coal was lost to the environment as waste. This inspired a handful of scientists to think deeply about the physical principles governing steam engines, seeking ways to burn less and get more. Over the course of many decades, their research gradually led to an iconic result that has become justly famous, the Second Law of Thermodynamics. In highly colloquial terms, the law declares that the production of waste is unavoidable. And what makes the second law vitally important is that while steam engines were the catalyst, the law is universally applicable. The second law describes a fundamental characteristic inherent in all matter and energy, regardless of structure or form, whether animate or inanimate. The law reveals, loosely, again, that everything in the universe has an overwhelming tendency to run down, to degrade, to wither. Stated in these everyday terms, you can see where Russell was coming from. The future seemingly holds a continued deterioration, a relentless conversion of productive energy into useless heat, a steady draining, so to speak, of the batteries powering reality. But a more precise understanding of the science reveals that this summary of where reality is headed obscures a rich and nuanced progression, one that has been underway since the Big Bang and will carry onward to the far future. It is a progression that helps explain our place in the cosmic timeline, clarifies how beauty and order can be produced against a backdrop of degradation and decay, and also offers potential ways, exotic though they may be, to sidestep the bleak end Russell envisioned. As it is this very science, involving concepts such as entropy, information, and energy, that will guide much of our journey. It is worth our while to spend a little time understanding it more fully. Steam engines. Far be it from me to suggest that the meaning of life will be found lurking in the sweaty depths of a clamorous steam engine, but understanding the steam engine's capacity to absorb heat from burning fuel and use it to drive recurrent motion in a locomotive's wheels or a coal mine's pump proves indispensable to grasping how energy, of any sort and in any context, evolves over time, and the way energy evolves has a deep impact on the future of matter, mind, and all structure in the universe. So let's descend from the lofty realms of life and death and purpose and meaning to the incessant chugging and clanking of an 18th-century steam engine. The scientific basis of the steam engine is simple but ingenious. Water vapor, steam, expands when heated and so pushes outward. A steam engine harnesses this action by heating a canister filled with steam that is capped by a snuggly fitting piston free to slide up and down along the canister's inner surface. As the heated steam expands, it pushes forcefully against the piston, and that outward thrust can drive a wheel to turn, or a mill to grind, or a loom to weave. Then, having expended energy through this outward exertion, the steam cools and the piston slides back to its initial position, where it stands ready to be pushed when the steam is heated again, a cycle that will repeat so long as there is burning fuel to heat the steam anew. 3. While history records the steam engine's central role in the Industrial Revolution, the questions it raised for fundamental science were just as significant. Can we understand the steam engine with mathematical precision? Is there a limit to how efficient its conversion of heat into useful activity can be? Are there aspects of the steam engine's basic processes that are independent of the details of mechanical design or materials used and thus speak to universal physical principles? In puzzling over these issues, the French physicist and military engineer Sadi Carnot launched the field of thermodynamics, the science of heat, energy, and work. You wouldn't have known it from sales of his 1824 treatise, Reflections on the Motive Power of Fire. 4. But while slow to catch on, his ideas would inspire scientists over the course of the following century to develop a radically new perspective on physics. A statistical perspective, the traditional scientific perspective, handed down in mathematical form by Isaac Newton, is that physical laws provide ironclad predictions for how things move. Tell me the location and velocity of an object at a particular moment, tell me the forces that are acting upon it, and Newton's equations do the rest, predicting the object's subsequent trajectory. Be it the moon pulled by Earth's gravity or a baseball you just whacked toward center field, observations have confirmed that these predictions are spot-on accurate. But here's the thing. If you took high school physics, perhaps you will recall that when we analyze the trajectories of macroscopic objects we generally, if quietly, invoke a great many simplifications. For the moon and the baseball we ignore their internal structure and imagine that each is just a single massive particle. It's a coarse approximation. Even a grain of salt contains about a billion molecules, and that's, well, a grain of salt. Yet as the moon orbits we generally don't care about the jostling motion of one or another molecule inhabiting the dusty sea of tranquility. As the baseball soars, we don't care about the vibration of one or another molecule residing in its cork core. The overall movement of the moon or the baseball as a whole is all we're after. And for that, applying Newton's laws to these simplified models does the trick. 5. These successes highlight the challenge faced by 19th-century physicists concerned with steam engines. The hot steam pushing against the engine's piston comprises an enormous number of water molecules, perhaps a trillion particles. We can't ignore this internal structure as we do in our analysis of the moon or the baseball. It is the motion of these very particles, slamming into the piston, bouncing off its surface, hitting the walls of the container, streaming back toward the piston again, that lies at the heart of the engine's workings. The problem is that there is no way that anyone, anywhere, however smart they may be and however formidable the computers they may use, can calculate all of the individual trajectories followed by such an enormous collection of water molecules. Are we stuck? You might think so. But as it turns out, we are saved by a change in perspective. Large collections can sometimes yield their own powerful simplifications. It is surely difficult, impossible really? to predict exactly when you will next sneeze. However, if we broaden our view to the larger collection of all humans on Earth, we can predict that in the next second there'll be roughly 80,000 sneezes worldwide. 6 The point is that by shifting to a statistical perspective, Earth's large population becomes the key, not the obstacle, to predictive power. Large groups often display statistical regularities absent at the level of the individual. An analogous approach for large groups of atoms and molecules was pioneered by James Clerk Maxwell, Rudolf Clausius, Ludwig Boltzmann, and many of their colleagues. They advocated jettisoning detailed consideration of individual trajectories in favor of statistical statements describing the average behavior of large collections of particles. They showed that this approach not only makes calculations mathematically tractable, but the physical properties it can quantify are the very ones that matter most. The pressure pushing on a steam engine's piston, for instance, is hardly affected by the precise path followed by this or that individual water molecule. Instead, the pressure arises from the average motion of the trillions upon trillions of molecules that slam into its surface each second. That's what matters. And that's what the statistical approach allowed the scientists to calculate. In our current era of political polls, population genetics, and big data more generally, the shift to a statistical framework might not sound radical. We've grown accustomed to the power of statistical insights extracted from studying large groups. But in the 19th and early 20th centuries, statistical reasoning was a departure from the rigid precision that had come to define physics. Bear in mind, too, that up through the early years of the 20th century there were still well-respected scientists who challenged the existence of atoms and molecules, the very basis of a statistical approach. Notwithstanding the naysayers, it didn't take long for statistical reasoning to prove its worth. In 1905, Einstein himself quantitatively explained the jittery motion of pollen grains suspended in a glass of water by invoking the continual bombardment by H2O molecules. With that success, you had to be one heck of a contrarian to doubt the existence of molecules. What's more, a growing archive of theoretical and experimental papers revealed that conclusions based on statistical analyses of large collections of particles, describing how they bounce around containers and thereby exert pressure on this surface, or acquire that density, or relax to that temperature, matched data so exquisitely that there was simply no room to question the explanatory power of the approach. The statistical basis for thermal processes was thus born. This was all a great triumph and has allowed physicists to understand not only steam engines but also a broad range of thermal systems, from Earth's atmosphere, to the solar corona, to the vast collection of particles swarming within a neutron star. But how does this relate to Russell's vision of the future, his prognostication of a universe crawling toward death? Good question. Hang tight. We're getting there, but we still have a couple of steps to go. The next is to use these advances to shed light on the quintessential quality of the future. It differs profoundly from the past. From this to that, the distinction between past and future is at once basic and pivotal to human experience. We were born in the past. We will die in the future. In between, we witness innumerable happenings that unfold through a sequence of events that, if considered in reverse order, would appear absurd. Van Gogh painted Starry Night but could not then lift the swirling colors through reverse brush strokes, restoring a blank canvas. The Titanic scraped along an iceberg and ripped open its hull but could not then reverse engines, retrace its path, and undo the damage. Each one of us grows and ages, but we cannot then turn back the hands of our internal clocks and reclaim our youth. With irreversibility being so central to how things evolve, you would think we could easily identify its mathematical origin within the laws of physics. Surely, we should be able to point to something specific in the equations that ensures that although things can transform from this to that, the math forbids them from transforming from that to this. But for hundreds of years the equations we've developed have failed to offer us anything of the sort. Instead, as the laws of physics have been continually refined, passing through the hands of Newton, classical mechanics, Maxwell, electromagnetism, Einstein, relativistic physics, and the dozens of scientists responsible for quantum physics, one feature has remained stable: the laws have steadfastly adhered to a complete insensitivity to what we humans call future and what we call past. Given the state of the world right now, the mathematical equation street unfolding toward the future or the past in exactly the same way, while that distinction matters to us, profoundly so, the laws shrug at the difference, assessing it as of no greater consequence than a stadium's game clock ticking off time elapsed or time remaining, which means that if the laws allow for a particular sequence of events to occur, then the laws necessarily permit the reverse sequence 2.7. As a student, when I first learned about this, it struck me as just shy of ludicrous. In the real world we don't see Olympic divers popping out of pools feet first and landing calmly on springboards. We don't see shards of stained glass jumping up from the floor and reassembling into a Tiffany lamp. Clips from films run in reverse are amusing for the very reason that what we see projected differs so thoroughly from anything we experience. And yet, according to the math, the events depicted in reverse-run clips are fully in keeping with the laws of physics. Why then is our experience so lopsided? Why do we only ever see events unfold in one temporal orientation and never the reverse? A key part of the answer is revealed by the notion of entropy, a concept that will be essential to our understanding of the cosmic unfolding. Entropy. A first pass. Entropy is among the more confusing concepts in fundamental physics, a fact that has not diminished the cultural appetite for freely invoking it to describe everyday situations that have evolved from order to chaos or, more simply, from good to bad. As colloquial usage goes, this is fine. At times, I've invoked entropy that way too. But as the scientific conception of entropy will guide our journey, and also lies at the heart of Russell's dark vision of the future, let's tease out its more precise meaning. Start with an analogy. Imagine you vigorously shake a bag containing 100 pennies and then dump them out on your dining room table. If you found that all 100 pennies were heads, you'd surely be surprised. But why? Seems obvious, but it's worth thinking through. The absence of even a single tail means each of the 100 coins, randomly flipping, bumping, and jostling, must hit the table and land heads up. All of them. That's tough. Getting that unique outcome is a tall order. By comparison, if we consider even a slightly different outcome, say in which we have a single tail, and the other 99 pennies are still all heads, there are 100 different ways this can happen. The lone tail could be the first coin, or it could be the second coin, or the third, and so on up to the 100th coin. Getting 99 heads is thus 100 times easier, 100 times more likely, than getting all heads. Let's keep going. A little figuring reveals that there are 4,950 different ways we can get two tails, first and second coins tails, first and third tails, second and third tails, first and fourth tails, and so forth. A little more figuring and we find that there are 161,700 different ways to have three of the coins come up tails, almost 4 million ways to have four tails, and about 75 million ways to have five tails. The details of the numbers hardly matter. It's the overall trend I'm driving at. Each additional tail allows for a far larger collection of outcomes that fit the bill. Phenomenally larger. The numbers peak at 50 tails, and 50 heads, for which there are about 100 billion possible combinations. Well, 1088913445464193334812497256 combinations. 8. Getting 50 heads and 50 tails is therefore about 100 billion times more likely than getting all heads. That's why getting all heads would be shocking. My explanation relies on the fact that most of us intuitively analyze the collection of pennies much as Maxwell and Boltzmann advocated analyzing a container of steam. Just as the scientists turned a cold shoulder to analyzing the steam molecule by molecule, we typically don't evaluate a random collection of pennies coin by coin. We hardly care or notice if the 29th penny is heads or the 71st is tails. Instead, we look at the collection as a whole, and the feature that catches our attention is the number of heads compared to the number of tails. Are there more heads than tails or more tails than heads? Twice as many. 3 times as many, roughly equal amounts. We can detect significant changes in the ratio of heads to tails, but random rearrangements that preserve the ratio, like flipping the 23rd, 46th, and 92nd coins from tails to heads while also flipping the 17th, 52nd, and 81st coins from heads to tails, are virtually indistinguishable. Consequently, I divvied up the possible outcomes into groups, each containing those configurations of coins that pretty much look the same, and I enumerated the membership of each group. I counted the number of outcomes with no tails, the number of outcomes with 1 tail, the number of outcomes with 2 tails, and so on, up to the number of outcomes with 50 tails. The key realization is that these groups do not have equal membership, not even close. That made it obvious why you'd be shocked for a random shake of the pennies to yield no tails, a group with precisely 1 member, slightly less shocked for a random shake to yield 1 tail, a group with 100 members, a touch less shocked still to find 2 tails, a group with 4,950 members, but you'd yawn if the shake yields a configuration that's half heads and half tails, a group with roughly 100 billion members. The greater the membership in a given group, the more likely it is that a random outcome will belong to that group. Group size matters. If this material is new to you, you may not realize that we have now illustrated the essential concept of entropy. The entropy of a given configuration of the pennies is the size of its group, the number of fellow configurations that pretty much look like the given configuration. 9 If there are many such lookalikes, the given configuration has high entropy. If there are few such lookalikes, the given configuration has low entropy. All else being equal, a random shake is more likely to belong to a group with higher entropy since such groups have more members. This formulation also connects with the colloquial uses of entropy I referenced at the outset of this section. Intuitively, messy configurations. Think of a chaotic desktop piled high with scattered documents, pens, and paper clips. Have high entropy because a great many rearrangements of the constituents all pretty much look the same. Randomly rearrange a messy configuration and it still looks messy. Orderly configurations. Think of a pristine desktop with all documents, pens, and paper clips neatly placed in their designated positions. Have low entropy because very few rearrangements of the constituents look the same. As with the pennies, high entropy beckons because messy arrangements far outnumber orderly ones. Entropy, the real deal. The pennies are particularly useful because they illustrate the approach scientists developed for dealing with the voluminous collection of particles constituting physical systems, whether water molecules flitting to and fro in a hot steam engine or air molecules drifting across the room in which you are now breathing. As with the pennies, we ignore the details of individual particles, whether any one particular molecule of water or air happens to be here or there is of little consequence, and instead group together those configurations of the particles that pretty much look the same. For the pennies, The criterion for lookalikes invoked the ratio of heads to tails because typically we are indifferent to the disposition of any particular coin, and generally take note only of the configuration's overall appearance. But what does pretty much look the same mean for a large collection of gas molecules? Think about the air now filling your room. If you're like me and the rest of us, you couldn't care less whether this molecule of oxygen is flitting by the window or that molecule of nitrogen is bouncing off the floor. You care only that each time you inhale there is an adequate volume of air to meet your needs. Well, there are a couple of other features you likely care about too. If the air's temperature was so hot that you scorched your lungs, you'd be unhappy. Or if the air's pressure was so high, and you hadn't equalized it with the air already in your Eustachian tubes, that you burst your eardrums, you'd be unhappy too. Your concern, then, is with the air's volume, the air's temperature, and the air's pressure. Indeed, these are the very macroscopic qualities that physicists from Maxwell and Boltzmann on through today care about too. Accordingly, for a large collection of molecules in a container, we say that different configurations pretty much look the same if they fill out the same volume, have the same temperature, and exert the same pressure. Much as with the pennies, we group together all look-alike configurations of the molecules and say that each member of the group gives rise to the same macrostate. The entropy of the macrostate is the number of such look-alikes, assuming you are not just now turning on a space heater, affecting temperature, or putting up an impermeable room divider, affecting volume, or pumping in additional oxygen, affecting pressure. The ever-evolving configuration of air molecules flitting to and fro in the room you are now inhabiting all belong to the same group. They all pretty much look the same, as they all yield the very same macroscopic features you are currently experiencing. The organization of particles into groups of lookalikes provides an extraordinarily powerful schema. Just as randomly tossed pennies are more likely to belong to a group with greater membership, with higher entropy, so too for randomly bouncing particles. The realization is as straightforward as its implications are far-reaching. Whether the bouncing particles are in a steam engine, in your room, or anywhere else, by understanding the typical features of the most commonplace configurations, those that belong to the groupings with the greatest membership, we can make predictions about the system's macroscopic qualities, the very qualities we care about. These are statistical predictions, to be sure, but ones with a fantastically high probability of being accurate. And the kicker is that we achieve all this while avoiding the insurmountable complexity of analyzing the trajectories of an absurdly large number of particles. To carry out the program we therefore need to sharpen our ability to identify commonplace, high entropy, versus rare, low entropy, particle configurations. That is, given the state of a physical system, we need to determine whether there are many or few rearrangements of the constituents that would leave the system looking pretty much the same. As a case study, let's visit your steam-filled bathroom just after you've taken a long hot shower. To determine the steam's entropy, we need to count the number of configurations of the molecules, their possible positions and their possible speeds, that all have the same macroscopic properties, that is, have the same volume, same temperature, and same pressure. 10 Carrying out the count mathematically for a collection of H2O molecules is more challenging than the analogous count for a collection of pennies, but is something most physics majors learn to do by their sophomore year. More straightforward, and more enlightening too, is working out how volume, temperature, and pressure qualitatively affect entropy. Volume first. Imagine that the flitting H2O molecules are tightly clustered in one tiny corner of your bathroom, creating a dense knot of steam. In this configuration, the possible rearrangements of the positions of the molecules will be sharply curtailed, as you move the H2O molecules around. You have to keep them within that knot, or else the modified configuration will look different. By comparison, when the steam is evenly spread throughout your bathroom, the game of molecular musical chairs is far less constrained. You can exchange the positions of molecules near the vanity with those floating by the light fixture, those near the shower curtain with those hovering by the window, and yet, overall, the steam will look the same. Note too that the bigger your bathroom, the greater the number of locations you have for sprinkling around the molecules, which also increases the number of rearrangements available. The conclusion, then, is that smaller and tightly clustered configurations of molecules have lower entropy, while larger and evenly spread configurations have higher entropy. Temperature next. At the level of molecules, what do we mean by temperature? The answer is well known. Temperature is the average speed of a collection of molecules. 11 Something is cold when the average speed of its molecules is low, and it is hot when the average speed is high. So determining how temperature affects entropy is tantamount to determining how the average molecular speed affects entropy. And much as we found with molecular positions, a qualitative assessment is close at hand. If the temperature of the steam is low, the allowed rearrangements of the molecular speeds will be comparatively few in number, to keep the temperature fixed, and thus ensure that the configurations all pretty much look the same. You have to offset any increase in the speeds of some molecules by a suitable decrease in the speeds of others. But the burden of having low temperature, low average molecular speed, is that you don't have a lot of room to decrease the speeds before hitting rock bottom, 0. The available range of possible molecular speeds is thus narrow, and so your freedom to rearrange the speeds is limited. By comparison, if the temperature is high, your game of musical chairs once again revs up, with a higher average. The range of molecular speeds, some larger than the average and some smaller, is much wider, providing greater latitude for mixing up the speeds while preserving the average. More rearrangements of the molecular speeds that all pretty much look the same means that higher temperature generally entails higher entropy. Finally, pressure. The pressure of the steam on your skin or on the bathroom walls is due to the impact of streaming H2O molecules that slam into these surfaces. Each molecular impact exerts a tiny push, and so the greater the number of molecules, the higher the pressure. For a given temperature and volume, pressure is thus determined by the total number of steam molecules in your bathroom, a quantity whose consequences for entropy can be worked out with the greatest of ease. Fewer H2O molecules in your bathroom, you took a shorter shower, means fewer rearrangements are possible, and so entropy is lower. More H2O molecules, you took a longer shower, means more rearrangements are possible, and so entropy is higher. To summarize, having fewer molecules, or having lower temperature, or filling a smaller volume results in lower entropy. Having more molecules, or having higher temperature, or filling a larger volume results in higher entropy. From this brief survey, let me underscore one way of thinking about entropy, lacking in precision but providing a useful rule of thumb. You should expect to encounter high entropy states because such states can be realized by a great many different arrangements of the constituent particles. They're typical, pedestrian, easily configured, a dime a dozen. By contrast, if you encounter a low entropy state, it should command your attention. Low entropy means there are far fewer ways the given macro state can be realized by its microscopic ingredients, and so such configurations are hard to come by, they're unusual, they're carefully arranged, they're rare. Step out of a long hot shower and find the steam uniformly spread throughout your bathroom. High entropy and totally unsurprising. Step out of a long hot shower and find the steam all clustered in a perfect little cube hovering in front of the mirror, low entropy and extraordinarily unusual. So unusual, in fact, that were you to encounter such a configuration, you should be extremely skeptical of the explanation that you've simply come upon one of those unlikely things that on occasion happen. That could be the explanation, but I'd bet my life it isn't. Just as you'd suspect there's a reason beyond mere chance that 100 pennies on your dining room table are all heads, such as someone judiciously flipped over each coin that landed tails, you should seek an explanation beyond mere chance for any low-entropy configurations you encounter. This reasoning applies even to the seemingly mundane, like coming across an egg or an anthill or a mug. The orderly, crafted, low-entropy nature of these configurations calls out for an explanation. That the random motion of precisely the right particles could just happen to coalesce into an egg or an anthill or a mug is conceivable, but far-fetched. Instead, we're motivated to find more convincing explanations, and of course we don't have far to search. The egg and the anthill and the mug each arise from particular forms of life arranging the otherwise random configuration of particles in the environment to yield orderly structures. How life is able to produce such exquisite order is a theme we will address in later chapters. For now, the lesson is simply that low-entropy configurations should be viewed as a diagnostic, a clue that powerful organizing influences may be responsible for the order we've encountered. In the late 1800s, armed with these ideas, many of his own devising, Austrian physicist Ludwig Boltzmann believed he could address the question that launched this section of our discussion: what distinguishes the future from the past? His answer relied on a quality of entropy articulated by the Second Law of Thermodynamics. Laws of thermodynamics. While entropy and the Second Law enjoy a great many cultural references, public nods to the First Law of Thermodynamics are less common. Yet to fully grasp the Second Law, it's good to grasp the First Law first. As it turns out, the First Law is widely known too, but under an alias. It's the law of energy conservation. Whatever energy you have at the beginning of a process is the same energy you'll have at the end of the process. You must be fastidious in your energy accounting, including all forms into which an initial cache of energy may have transformed, such as kinetic energy, energy of motion, or potential energy, stored energy, as in a stretched spring, or radiation, energy carried by fields, like the electromagnetic or gravitational fields, or heat, the random jittery motion of molecules and atoms. But if you keep track carefully, the First Law of Thermodynamics ensures that the energy balance sheet will balance. 12. The Second Law of Thermodynamics focuses on entropy. Unlike the First Law, the second is not a law of conservation, it is a law of growth. The Second Law declares that over time there is an overwhelming tendency of entropy to increase. In colloquial terms, special configurations tend to evolve toward ordinary ones. Your carefully pressed shirt becomes creased and wrinkled, or order tends to descend into disorder. Your organized garage degenerates into a haphazard mess of tools, storage boxes, and sporting equipment. While this depiction provides fine intuitive imagery, Boltzmann's statistical formulation of entropy allows us to describe the Second Law with precision and, just as important, gain a clear understanding of why it's true. It comes down to a numbers game. Consider again the pennies. If you carefully arrange the pennies so they are all heads, a low entropy configuration, and then subject them to a little shaking and jostling, you expect to get at least a few tails, a higher entropy configuration. If you shake them further, it's conceivable that you'll get back to all heads, but that would require the jostling to be just right, to be so perfectly attuned that it flips back only those few coins that happen to be tails. That's extraordinarily improbable. It is fantastically more likely that the jostling will instead flip a random collection of the pennies. Some of the few coins that were tails might revert to heads, but of the coins that were heads, many more will become tails. So straightforward logic, no fancy math, no unduly abstract ideas, reveals that if you begin with all heads, random shaking will drive an increase in the number of tails. An increase, that is, of entropy. The progression toward a greater number of tails will continue until we reach a roughly 50-50 heads-tails split. At that point, the jostling will tend to flip about as many heads to tails as tails to heads, and so the pennies will spend most of their time migrating among the members of the most populous, highest entropy groups. What's true for the pennies is true more generally. Bake bread and you can be sure that the aroma will shortly fill rooms far from the kitchen. At first, the molecules released as the bread bakes are clustered near the oven, but those molecules will gradually disperse. The reason, similar to our explanation with the pennies, is that there are many more ways for the aroma molecules to spread compared with ways for them to cluster. It is thus overwhelmingly more probable that through random bumping and jostling the molecules will waft outward as opposed to clump inward. The low entropy configuration of molecules clustered near the oven thus naturally evolves toward the higher entropy state in which they are spread throughout your house. 13. Saying it yet more generally, if a physical system is not already in the highest entropy state available, it is overwhelmingly likely that it will evolve toward it. The explanation, illustrated well by the bread's aroma, rests on the most basic reasoning, because the number of configurations with more entropy is enormously greater than those with less entropy. By the very definition of entropy, the odds are enormously larger that random jostling, the relentless bumping and vibrating of atoms and molecules, will drive the system toward higher entropy, not lower. The progression will continue until we reach a configuration with the highest entropy available. From that point onward, the jostling will tend to drive the constituents to migrate among the, typically, gargantuan number of configurations of the highest entropy states. 14. That's the second law of thermodynamics, and that's why it is true. Energy and entropy. The discussion might lead you to think that the first and second laws are thoroughly distinct. After all, one focuses on energy and its conservation, the other on entropy and its growth. But there's a deep connection between them, highlighting a fact implicit in the second law that we will return to repeatedly. All energy is not created equal. Consider, as an example, a stick of dynamite. Because all the energy stored in the dynamite is contained in a tight, compact, orderly chemical package, the energy is easy to harness. Place the dynamite where you want its energy deposited and light the fuse. That's it. Post-explosion, all of the dynamite's energy still exists. That's the first law in action. But because the dynamite's energy has been transformed into the rapid and chaotic motion of widely dispersed particles, harnessing the energy is now extremely difficult. So, although the total amount of energy doesn't change, the character of the energy does. Before the explosion, we say that the dynamite's energy is high quality. It's concentrated and easy to access. After the explosion, we say that the energy is low quality, it's spread out and difficult to utilize. And since the exploding dynamite fully abides by the second law, going from order to disorder, from low entropy to high entropy, we associate low entropy with high quality energy and high entropy with low quality energy. Yes, I know, it's a lot of highs and lows to keep track of. But the conclusion is pithy. Whereas the first law of thermodynamics declares that the quantity of energy is conserved over time, the second law declares that the quality of that energy deteriorates over time. Why then is the future different from the past? The answer, apparent from what we've now developed, is that the energy powering the future is of lower quality than that powering the past. The future has higher entropy than the past, or at least that is what Boltzmann proposed. Boltzmann and the Big Bang. Boltzmann was surely onto something. But there is a subtle clarification to the second law whose implications, truth be told, took some time even for Boltzmann to appreciate fully. The second law is not a law in the traditional sense. The second law does not absolutely preclude entropy from decreasing. It declares only that such a decrease is unlikely. For the pennies, we've quantified this. Compared with the sole configuration with all heads, it is 100 billion times more likely that random shaking will yield a configuration with 50 heads and 50 tails. Shake that high entropy configuration again, and getting a lower entropy configuration such as all heads is not forbidden, but because of the highly skewed odds, in practice it doesn't happen. For an everyday physical system made from far more than 100 constituents, the odds against entropy decreasing become all the more daunting. As bread bakes, it releases billions upon billions of molecules. Configurations in which those molecules spread throughout your home are spectacularly more numerous than those in which they collectively stream back toward the oven. Through their random jostling and bumping, the molecules could retrace their steps, find their way back to the loaf, fully undo the cooking process, and leave you with a mound of cold raw dough. But the odds of that happening are closer to zero than the likelihood of splattering paint on a canvas and replicating the Mona Lisa. Even so, the point is that were such an entropy reversing process to happen, it would not contravene the laws of physics. While spectacularly unlikely, the laws of physics do allow entropy to go down. Don't get me wrong, I'm not bringing this up to suggest we might one day uncook bread or witness a car uncrash or see a document unburn. Instead, I'm stressing an important point of principle. I explained earlier that the laws of physics put future and past on equal footing. The laws thus ensure that physical processes that unfold in one temporal sequence can unfold in reverse. And since those very same laws govern everything, including the physical processes responsible for how entropy changes over time, it would indeed be curious, erroneous really, to find that those laws only allow entropy to increase. They don't. All the entropically increasing processes you've experienced day in and day out during your entire life, from the mundane of a shattering glass to the profound of bodily aging, can happen in reverse. Entropy can decrease. It's just ridiculously unlikely. So where does this leave our quest to explain why the future is different from the past? Well, given a configuration today of less than maximum entropy, the second law shows that the future is overwhelmingly likely to be different because entropy is overwhelmingly likely to increase. Configurations of matter that have less than the maximum possible entropy are chomping at the bit to proceed to higher entropy. And with that observation, some exploring the difference between past and future rest easy, reckoning that their work is done. But the work is not done. Just as importantly, we need to explain how it is that we find ourselves today in such a special, unlikely, surprising state of less than maximum entropy, a universe replete with orderly structures from planets and stars to peacocks and people. Had that not been the case, had today's configuration been the expected, ordinary, unsurprising state of maximum entropy, then with great odds the universe would continue to inhabit such a state, yielding a future no different from the past. Like a bag of pennies jostling through the enormous number of configurations with roughly 50 heads and 50 tails, the universe would relentlessly meander through the enormous landscape of its highest entropy configurations, widely dispersed particles streaming this way and that across space, a cosmic version of your uniformly steam-filled bathroom. 15 Today's state of less than maximum entropy is, luckily for us, far more interesting. It provides the opportunity for particles to join into structures and for macroscopic change to occur. And so we are led to ask, how did today's less than maximum entropy state come to be? Dutifully following the second law, we conclude that today's state derives from yesterday's, even lower entropy state. And that state, we envision, derives from the day before yesterday's still lower entropy state, and so on. yielding a trail of ever-decreasing entropy taking us ever farther back in time until we finally reach the Big Bang, a highly ordered, exceedingly low entropy starting point at the Big Bang is why today's universe is not entropically maxed out, allowing for an eventful future that differs from the past. Can we go further and explain why the beginning of the universe was so ordered? We will come back to this question in the next chapter, where we'll explore cosmological theorizing. For now we note that our survival requires order, from our internal molecular organization supporting a wealth of life-sustaining functions, to the food sources that provide us with high-quality energy, to the crafted tools and habitats that are essential for our continued existence. Without an environment chock full of low-entropy ordered structures, we humans would not be here to notice heat and entropy. I began this chapter with Bertrand Russell lamenting a universe subject to relentless decline. With the second law's declaration of rising entropy, we have now caught a glimpse of what inspired his dark prophecy. Think of rising entropy as increasing disorder and you have the gist of it. But to fully appreciate the future challenges that will face life, mind, and matter, a theme we will amply explore in subsequent chapters, we need to establish a link between the modern description of the second law of thermodynamics as I have laid it out and the original formulation developed in the mid-1800s. In that earlier version, the second law codified what was obvious to anyone working with steam engines: the process of burning fuel to run a machine always produces heat and waste, degradation. However, as the earlier version made no mention of counting configurations of particles and made no use of probabilistic reasoning, it might seem a world away from the statistical statement of entropic growth that we've been developing. But there is a deep and direct connection between the two formulations, one that reveals why the steam engine's conversion of high-quality energy into low-quality heat is illustrative of a ubiquitous degradation taking place throughout the cosmos. I'll explain the link in 2 steps. First, let's look at the relationship between entropy and heat. Then, in the next section, we will tie together heat and the statistical statement of the second law. Grab hold of a sauté-pan's hot handle and it feels like heat is flowing to your hand. But does anything actually flow? There was a time long ago when scientists thought the answer was yes. They envisioned a fluid-like substance, called caloric, which would flow from hotter locations to cooler ones much like a river flows from upstream to downstream. In time, the more refined understanding of matter's ingredients provided a different description. When you grasp the pan's handle, its faster-moving molecules collide with the slower-moving molecules in your hand, on average causing the speed of those in your hand to go up and those in the handle to go down. You sense the increased speed of the molecules in your hand as warmth. The temperature of your hand has increased. Correspondingly, the slower speed of the molecules in the handle means its temperature has decreased. What flows, then, is not a substance. The molecules in the handle stay in the handle, and those in your hand stay in your hand. Instead, much as information flows from one person to the next in a game of telephone, molecular agitation flows from molecules in the handle to those in your hand when you grab it. And so, whereas matter itself does not flow from handle to hand, a quality of matter, average molecular speed, does. That is what we mean by the flow of heat. The same description applies to entropy. As the temperature of your hand increases, its molecules bounce around more quickly, the range of their possible speeds widens, increasing the number of attainable configurations that pretty much look the same. And so the entropy of your hand increases too. Correspondingly, as the temperature of the handle decreases, its molecules move slower, the range of their possible speeds narrows, decreasing the number of attainable configurations that pretty much look the same, and so the entropy of the handle decreases. Whoa, entropy decreases? Yes, but this has nothing to do with rare statistical flukes like dumping a bag of pennies and getting all heads. As described in the previous section, the entropy of the hot handle will decrease every time you grab it. The simple yet vital point the Sauté pan illustrates is that the second law's dictum of entropy increase refers to the total entropy of a complete physical system, which necessarily includes everything with which the system interacts. Since your hand interacts with the pan's handle, you can't apply the second law to the handle on its own. You must include both the handle and your hand, and, to be more precise, the entire pan, the stove, the surrounding air, and so on. And a careful accounting shows that the increase in the entropy of your hand outstrips the decrease in the entropy of the handle, ensuring that the total entropy does indeed go up. So, much as with heat, there is a sense in which entropy can flow. For the pan, it flows from the handle to your hand. The handle becomes a little more ordered and your hand becomes a little less ordered. Again, the flow is not in the form of a tangible substance that was initially in the handle and has now moved to your hand. Rather, the entropy flow denotes an interaction between the molecules in the handle and those in your hand that affects the properties of each. In this case, it changes their average speeds, their respective temperatures, and that, in turn, affects the entropy they each contain. As the description makes manifest, the flow of heat and the flow of entropy are intimately connected. To absorb heat is to absorb energy that is carried by random molecular motion. That energy, in turn, drives the receiving molecules to move more quickly or spread more widely, thus contributing to an increase in entropy. The conclusion, then, is that to shift entropy from here to there, heat needs to flow from here to there. And when heat flows from here to there, entropy shifts from here to there. In short, entropy rides the wave of flowing heat. With this understanding of the interrelationship between heat and entropy, let's now revisit the second law, heat, and the second law of thermodynamics. Explaining why we experience events unfurling in one direction but not the reverse brought us to Boltzmann and his statistical version of the second law. Entropy is overwhelmingly likely to increase toward the future, making reverse run sequences, in which entropy would decrease, fantastically improbable. How does this relate to the earlier formulation of the second law, inspired by the steam engine, which was phrased in terms of the relentless production of waste heat by physical systems? The connection is that the two starting points, reversibility and steam engines, are tightly linked. The reason is that the steam engine relies on a cyclical process. A piston is thrust forward by expanding steam and is then reset to its original position, where it awaits the next thrust. The steam, too, reverts to its original volume, temperature, and pressure, as must all of the engine's vital parts, readying the engine to heat back up and thrust the piston once again. While none of this requires the ridiculously improbable unfolding in which every molecule finds its way back to exactly the same spot or acquires exactly the same speed as it had at the start of the previous cycle, it does require that the overall arrangement, the engine's macrostate, returns to the same form to initiate each subsequent cycle. What does that imply for entropy? Well, since entropy is a count of the microscopic configurations that present as the same macrostate, if the macrostate of the steam engine is reset at the start of each new cycle, then its entropy must be reset too, which means that the entropy the steam engine acquires during a given cycle, as it absorbs heat from the burning fuel, as it generates additional heat through friction of its moving parts, and so on, must all be expelled to the environment by the time the cycle concludes. How does the steam engine accomplish this? Well, we've seen that to transfer entropy you must transfer heat. Thus, for the steam engine to reset itself for the next cycle, it must release heat into the environment. That's the historical statement of the second law of thermodynamics, the inevitable expunging of waste heat into the environment, the very degradation that so weighed on Bertrand Russell, now derived from the statistical version of the second law. 16. This is the destination I've been heading for, so feel free to jump to the next section. But if you have the patience, there is one detail I'd be remiss not to mention. You might wonder, if the steam engine absorbs heat from the burning fuel, thus absorbing entropy, only to release heat to the environment, thus releasing entropy, how does it have any remaining energy to accomplish useful tasks, like powering a locomotive? The answer is that the steam engine releases less heat than it absorbs and yet is still able to fully purge the entropy it has built up. Here's how it goes. The steam engine absorbs heat and entropy from the burning fuel and releases heat and entropy to the cooler environment. The temperature difference between the fuel and the environment is what's vital. To see why, imagine turning on two identical space heaters, one in a room that's frigid and the other in a room that's hot. In the frigid room, the cold molecules of air are jolted by the space heater, causing them to move faster and disperse widely, and so their entropy increases significantly. In the hot room, the air molecules are already moving fast and flitting widely, and so the space heater only slightly increases their entropy. It is kind of like turning up the beat at a wild New Year's party and barely noticing that the revelers dance a touch more quickly, but turn up the beat at the Thiksay monastery, enticing monks to break from their meditative practice and start crumping, and you would readily see the change. So even though the two space heaters are identical, the entropy they transfer to their surroundings is different. While each generates the same amount of heat, the space heater in the cooler environment transfers more entropy. A cooler environment thus amplifies a given amount of heat received into a larger entropic increase. With that realization, we see that the steam engine can discharge all of the entropy it acquires from the hotter fuel by expelling only part of that heat to the cooler environment. The remaining heat is then available to drive the steam to expand, pushing the piston and accomplishing useful work. That's the explanation, but don't let the details cloud the larger conclusion. Over time, physical systems will, with fantastic likelihood, evolve from configurations of lower entropy toward configurations of higher entropy. If a system, like a steam engine, seeks to maintain its structural integrity, it must stave off the natural drive toward increased entropy by transferring the entropy it builds up to its surroundings. To do so, the engine must release waste heat to the environment. The Entropic Two Step. If you carefully think through the steps we've followed, you'll see that although the steam engine has been peppered throughout, our conclusions transcend this 18th century starting point. The essence of our analysis is a close accounting of entropy, and that accounting can be carried out in any context. This is a key realization, because the shifting of entropy from the steam engine to its surroundings through the release of heat is but one version of an utterly ubiquitous process we will encounter as we follow the unfolding of the cosmos. I call it the Entropic Two Step, by which I mean any process in which the entropy of a system decreases because it shifts a more than compensating increase in entropy to the environment. The two-step ensures that even though entropy may decrease here, it will increase there, securing the net entropic increase we expect based on the second law. The Entropic Two-Step lies at the heart of how a universe heading toward ever greater disorder can nevertheless yield and support ordered structures like stars, planets, and people. A theme we will encounter repeatedly is that when energy flows through a system, like the energy from burning coal flowing through the steam, driving work, and then exiting to the surrounding environment, it carries away entropy and can thus sustain or even produce order in its wake. It is this entropic dance that will choreograph the rise of life and mind, as well as most everything that minds deem to matter. You are a steam engine, with the importance of resetting the entropy each time a steam engine goes through a cycle. You might wonder what would happen if the entropy reset were to fail. That's tantamount to the steam engine not expelling adequate waste heat, and so with each cycle the engine would get hotter until it would overheat and break down. If a steam engine were to suffer such a fate, it might prove inconvenient but, assuming there were no injuries, would likely not drive anyone into an existential crisis. Yet the very same physics is central to whether life and mind can persist indefinitely far into the future. The reason is that what holds for the steam engine holds for you. It is likely that you don't consider yourself to be a steam engine or perhaps even a physical contraption. I, too, only rarely use those terms to describe myself. But think about it. Your life involves processes no less cyclical than those of the steam engine. Day after day, your body burns the food you eat and the air you breathe to provide energy for your internal workings and your external activities. Even the very act of thinking, molecular motion taking place in your brain, is powered by these energy conversion processes. And so, much like the steam engine, you could not survive without resetting your entropy by purging excess waste heat to the environment. Indeed, that's what you do. That's what we all do, all the time. It's why, for example, the military's infrared goggles designed to see the heat we all continually expel do a good job of helping soldiers spot enemy combatants at night. We can now appreciate more fully Russell's mindset when imagining the far future. We are all waging a relentless battle to resist the persistent accumulation of waste, the unstoppable rise of entropy. For us to survive, the environment must absorb and carry away all the waste, all the entropy, we generate. Which raises the question, does the environment, by which we now mean the observable universe, provide a bottomless pit for absorbing such waste? Can life dance the entropic two-step indefinitely? Or might there come a time when the universe is, in effect, stuffed and so is unable to absorb the waste heat generated by the very activities that define us, bringing an end to life and mind? In the lachrymose phrasing of Russell, is it true that all the labors of the ages, all the devotion, all the inspiration, all the noonday brightness of human genius, are destined to extinction in the vast death of the solar system, and that the whole temple of man's achievement must inevitably be buried beneath the debris of a universe in ruins? 17. These are among the central questions we will explore in coming chapters. But we've jumped a little ahead of ourselves. Before we discuss life and mind, let's understand how entropy and the second law play out in the formation of environments necessary for life and mind to take hold. For that, we head back to the Big Bang. A note about the author. Brain Greene is a professor of physics and mathematics at Columbia University and is renowned for a number of groundbreaking discoveries in string theory. He is the author of the New York Times best-selling books The Elegant Universe, The Fabric of the Cosmos, and The Hidden Reality. Greene hosted 2 award-winning Nova miniseries based on his books and is also a co-founder of the World Science Festival. With his wife and children, he lives in Andes, New York, and in New York City.